Welcome back to the Deep Dive. This is the show where we take a monumental stack of complex research, we tear it apart, and we give you the truly actionable, well-informed knowledge that you need right now.
That's right.
Today, we are going deep into the code intelligence era. And this is a topic that's moving so fast, it's really leaving the world of theory and entering the world of concrete, repeatable blueprints.
It really is. And our mission today is, well, it's explicitly focused on the practice. We're here to distill this huge body of work down into a set of recipes, practical, repeatable recipes for actually building, customizing, and deploying these code-generating models.
So not just the what, but the how.
Exactly, the how.
Right.
We're covering everything. Which model do you choose? How do you curate verifiable data? How do you actually apply supervised fine-tuning and reinforcement learning? And maybe most importantly, how do you build and secure autonomous agents in a real-world workflow?
And when you look at the timeline in the source material, the speed of this shift is it's astounding. We spent decades from the 60s to, 2020 in the human-driven coding era.
Right. Manual.
Then, just a few years ago, we hit this AI-assisted phase. Think, Copilot giving you some boilerplate code.
A suggestion engine, basically.
Exactly. But the research we're looking at today, it confirms we are accelerating and fast toward this AI-driven era. We're talking 2025 and beyond.
And that's a fundamental shift. It's the difference between an editor suggesting a line of code and a system that can autonomously take a complex GitHub issue that spans multiple files.
Understand it,
resolve it, submit a pull request, and pass all the CI tests without a human ever touching it. The focus has completely moved from just prediction to system-level reliability and verifiable accuracy.
And the ironclad security you'd need to actually deploy something like that.
You have it.
So if you're listening to this, if you're a curious learner, a software leader, maybe a researcher mapping out your next project, our goal here is to give you a clear, step-by-step algorithm.
A recipe book.
A recipe book for model selection and the precise, optimized training recipes you need, SFT and RL, to get state-of-the-art performance. We want to transform this abstract research into practical know-how you can use.
Let's do it.
Okay, let's unpack this. We have to start at the absolute foundation. Before you even think about training data or hyperparameters, you have to decide what kind of beast are you actually going to build?
Right.
Which architectural trade-offs are defining this current generation of code LLMs?
This choice, it's now the absolute core of the recipe. We are officially past the time when a dense transformer was the one and only answer.
The one-size-fits-all approach is dead.
It's dead. Your model choice now dictates your fundamental trade-offs. We're talking efficiency, latency, how you handle context, and just raw capacity.
So let's talk about that capacity. The major architectural shift that's dominating the conversation, especially for people who just want maximum power, is the rise of sparsity. We're talking mixture of experts, or MOE.
MOE.
From a practical standpoint, why did MOE become so essential in the code space? I mean, code demands incredible precision.
It does. And the core insight of MOE is this really elegant solution to what we call the capacity efficiency paradox.
Okay, break that down for me.
So to learn the massive sparse landscape of programming, all the logic, all the semantic relationships, all the weird little quirks of thousands of libraries models, need a frankly astronomical number of parameters.
We're talking trillions sometimes.
Potentially. And a dense model of that size is it's impossible to run. It's a fantasy. So MOE introduces something called conditional computation, meaning for any given piece of input, any token, only a small specific subset of the total parameters, these are called experts, is actually activated.
Ah, so you get the brain power of the whole thing without the cost of running the whole thing.
Exactly. You get the representational power of a massive model, but you only pay the computational cost of a much smaller one. You can see it in the numbers. DeepSeek V2, for instance, has 236 billion total parameters.
Which is huge.
Huge, but it only activates about 21 billion per token. And DeepSeek V3 is even more extreme. We're talking 671 billion total, with only 37 billion active at any one time.
So the magic is really in the router then. The thing that directs traffic to the right expert.
That's the secret sauce. It's a big architectural investment to get that right, but we're seeing it adopted basically everywhere now. It's the new high-capacity standard.
Right. GLM 4.5, you mentioned Quinn, DeepSeek, and the source notes, the entire Llama 4 series is built on this.
The entire series. And what's more, it works synergistically. MOE isn't just a standalone trick. It pairs really well with other efficiency features.
Like what? The source mentions long context handling and KV cache compression. I want to understand that. Why is KV cache compression even needed? And how does MOE help with it?
Okay, so the KV cache is basically the model's short-term memory. It stores key and value representations of tokens it's already seen to speed up generating the next one.
Right, in autoregressive decoding.
Exactly. But the longer your context window, the more code you feed it, the faster that cache grows, and it eats up incredibly expensive GPU memory, so you need compression to shrink it down.
And MOE helps with that
Because even though the total model is huge, the active part is small. This lets a MOE model handle much longer context more efficiently than a dense model of the same total size, especially when you pair it with techniques that aggressively prune or quantize those cache elements. It's a really powerful paradigm for scaling up in a production environment.
Okay, but MOE requires just an enormous amount of hardware up front. What if your top priorities are, say, low latency and a minimal memory footprint during inference? What are the alternatives?
Then you have to look at recurrent and state space models. These architectures are making a comeback. They're specifically designed to eliminate that quadratic scaling bottleneck of the standard transformer.
The O of n squared problem.
The O of n squared problem, where memory and compute complexity just explodes with the length of the sequence.
So how do they solve it?
Well, recurrent architectures like RWKV and RetNet, they get you to linear time decoding complexity. That's O of n. RWKV is really clever. It trains in parallel, which is fast like a transformer, but its inference is recurrent. It only activates a constant size state at each step.
And RetNet.
Retentive networks, or RetNet, also trains in parallel, but it can do inference either recurrently or in chunks. This makes it super robust for processing these extremely long sequences, like an entire code base with linear time and memory.
And then there's the one that's been making all the headlines, Mamba.
Right. Mamba brings in what are called selective state space models, or SSMs. The unique thing here is that Mamba's parameters are input dependent.
What does that mean in practice?
It means the model dynamically changes its own state based on the content it's seeing. It can learn to selectively prioritize or even filter out information over very long ranges. This gives you that linear time decoding and very high throughput. It's often more efficient than a transformer while staying super competitive on tough code tasks.
So those are all about, deterministic left-to-right generation, but the source also goes into diffusion-based models, which feels like a completely different way of thinking about code.
It is a totally different paradigm. Diffusion LMs, they don't do token-by-token decoding. Instead, they use an iterative denoising process.
So it starts with noise and refines it.
Exactly. It starts with a completely noisy, nonsensical sequence, and then refines it over many, many steps until valid code emerges. You see this in models like ELIDA, Gemini Diffusion, and Mercury Coder.
What's the trade-off? That sounds computationally expensive, but there must be a big upside.
The trade-off is absolutely inference speed. You usually need a lot of sampling steps to get to the final output, so it can be slower than a single-pass autoregressive model.
But the benefit is?
The massive benefit is strong global control over the generated code. Because the model is working on the whole sequence at once, iteratively, it can enforce global constraints, like making sure the code adheres to a specific API or a complex file structure way more effectively than a model that's just thinking one token at a time.
And the training is parallelizable, I assume.
Highly parallelizable. Mercury Coder specifically frames coding as parallel multi-token denoising to try and get around that sequential latency problem.
It really sounds like the community is realizing that no single mechanism is optimal for everything. Which brings us to, I guess, the inevitable conclusion. The hybrid approach. Trying to get the best of all worlds.
Exactly. Hybrid architectures don't rely on just one mechanism. They interleave complementary operators. Jamba is a great example. It weaves together standard transformer attention blocks with Mamba layers and often uses MOE for its feed-forward networks.
But the system architect can kind of dial in the trade-offs they want.
Precisely. You can intelligently balance quality, context length, and throughput depending on what you're building.
And we've seen models like QuinnNext really pushing the context length boundaries with this kind of strategy.
Qwen3Next is a perfect example. It's using a hybrid attention design, mixing these gated DeltaNet-style linear operators, which are optimized for super long-range dependencies, with standard attention and sparse MOE.
And their goal is pretty audacious.
It is. They're targeting contexts of 256,000 tokens or more with a very low number of active parameters. We're seeing this fusion everywhere. DeepSeek v3.2x is fusing MOE with other attention techniques. The whole field is racing towards long context efficiency by combining the strengths of multiple architectures.
So what's fascinating here is that a clear algorithm for choosing an architecture is starting to emerge. It's not just pick the biggest one.
Not anymore. It's a clear trade-off. If you are going for maximum raw, complex reasoning capacity, you choose MOE and you accept that it's going to be harder to tune.
And if you're optimizing for, say, a streaming application with ultra-low latency and a massive context window,
You go down the recurrent or the hybrid path. Practitioners now have to align their architectural choice directly with their deployment constraints. It's become a real tactical decision.
that makes a ton of sense.
Okay.
But I have to ask, for a practitioner, doesn't introducing Mamba layers and MOE experts and attention blocks create a more fragile system to optimize? More moving parts means more things can break right.
That's an excellent point, and it is the core challenge of hybrid models. They offer peak theoretical efficiency, but they introduce a ton of complexity in training. Stabilization and alignment become much harder.
So it's a balancing act.
It is. As we'll get into with SFT, these advanced architectures often need much more precise and prolonged hyperparameter tuning to make sure all those different parts, the router, the mama state, the attention heads, are all learning in harmony. Simplicity often wins for a quick, low compute deployment, but complexity is winning the race for the maximum performance ceiling.
I think I'll stick to a dense model for my side project then. Okay, so we have the architecture in mind. Now we need to talk about the fuel. The data foundation is the next critical step in the recipe.
And the specialized training objectives the models use to learn from that data.
You really can't talk about training a state-of-the-art code LLM without talking about sourcing high-quality code data. And the Stack dataset family from the BigCode collaboration. I mean, that's the foundation for almost everything.
It really is. The Stack V1, with 3.1 terabytes of permissively licensed code across 358 languages, was just a monumental achievement. But it wasn't just about the volume.
It was the methodology.
It was the rigorous methodology they used to deal with licensing and legal issues. They used this strict two-stage deduplication strategy.
What did that entail?
The first stage was about quality getting rid of exact or near-exact duplicates to stop the model from overfitting. But the second stage, which was crucial for legality, focused on only sourcing from GitHub repos that had licenses explicitly permitting redistribution.
So they built a legally sound foundation from the start.
A safe, compliant data set that the whole research community could use without worry. It was vital.
So the Stack provided the volume and the compliance. But then the community realized they needed more refinement, specifically to prevent benchmark cheating.
That's where StarCoder data comes in. It's a highly curated version of the Stack v1.2. And the critical quality control step here was this additional meticulous cleaning and decontamination.
Specifically targeting what?
Specifically targeting common evaluation benchmarks, human eval, MBPP, things like that. This step is to make sure your training data doesn't accidentally contain the answers to your tests.
Which would obviously invalidate your results.
Completely. So at 783 gigabytes, StarCoder data might be smaller, but its quality is arguably the gold standard right now, especially since they augmented it with contextual data from GitHub issues and commits.
So it's not just learning code, it's learning the process of coding.
Exactly. The conversation, the bug reports, the fixes.
Okay, so once you have this massive, clean, contextual data set, the model needs to learn specific tricks that go beyond just predicting the next word.
Beyond next token prediction, or NTP.
Right. What are the specialized objectives that are shaping pre-training now?
The two that are basically mandatory now are multi-token prediction, MTP, and fill in the middle, FIM.
MTP seems straightforward.
It's the simpler one. Instead of predicting just one token, the model predicts a whole chunk of consecutive tokens. This just boosts generation speed and helps with coherence when it's writing out whole lines or blocks of code.
But FIM is where it gets really interesting because fill in the middle is arguably the single biggest contributor to modern developer utility. It's what turns the model from a basic generator into an intelligent IDE companion.
It absolutely is. FIM is essential because it lets the model predict a missing chunk of code based on both what came before the cursor, the prefix, and what comes after the cursor, the suffix.
And that's the magic behind intelligent autocompletion anywhere in a file.
It's the cornerstone of it.
So how did Code Llama actually implement this? The source mentions these PSM and SPM formats, which sounds like a crucial detail for the recipe.
It is. The implementation relies on structuring the training data in a very specific way. They had to teach the model to handle two different formats using a set of 4 special tokens.
Okay, what are they?
FemPrefix, FemSuffix, FemMiddle, and FemPad.
And the 2 formats.
The first is PSM, prefix, suffix, middle. So if your cursor is near the end of a file, you give the model the prefix, a separator token, the suffix, which might just be a closing brace, and then the model is trained to generate what goes in the middle.
And the other one, SPM.
Suffix, prefix, middle. This is often used when the model needs to prioritize the context from what comes after the cursor, maybe the structure of the next function, before it generates the code in the middle.
Can you give me a concrete example? Let's say I'm defining a normalize function in Python.
Perfect. So you start typing def normalize nums, that's your prefix. Then you jump ahead and type the last line, return out, that's your suffix. In a PSM format, the input to the model might look like this. Prefix token def normalize nums. Suffix token return out middle token. The model's job is to predict all the calculation steps, the variance, the mean, all of it, that should go right after that middle token to complete the function.
And by training on this alongside standard prediction, it just learns to do this automatically.
It learns this deep, intelligent completion ability directly during inference. No extra fine-tuning needed just for that. It's baked in.
That level of detail is exactly what makes this actionable. Okay, so moving from objectives to the economics of training, the source brings up these crucial nuances about scaling laws for code. And it basically says we shouldn't waste our compute budget by treating all programming languages equally.
That's a critical insight for anyone trying to do this efficiently. There is very pronounced non-uniform scaling among different languages. The research found that different languages have distinct scaling exponents, which they call alpha D.
What does that exponent, alpha D, represent in practical terms?
It represents how much performance gain you get for doubling the amount of data you train on. So a high alpha D means the language really, really benefits from more data.
And the research found that languages like Python, C#, and TypeScript are high alpha D.
They are. They require substantially more data to reach their peak performance, probably because their semantic structure and massive ecosystems just demand more and more examples.
And the lower exponent languages.
Those are languages like Java and Go. They're low alpha D. They saturate much faster.
Why that?
It's likely linked to things like stricter typing, more redundancy, or just a higher proportion of boilerplate code. Once the model learns the core patterns of Java, throwing twice as much data at it gives you rapidly diminishing returns compared to doing the same for Python.
So the fundamental takeaway for anyone building a multilingual model is crystal clear. Stop allocating your training budget uniformly across languages.
Absolutely. The recipe is to allocate your token budget proportionally to these language-specific scaling exponents. This optimization-guided approach significantly outperforms a uniform split with the same compute budget. It's a massive advantage in cost efficiency and overall model performance. So once you've established that generalized knowledge in pre-training, the syntax, the structure, the FEM capability, we move on to supervised fine-tuning, or SFT.
This is the alignment step.
This is the alignment step. It transforms the model from this general knowledge base into a practical instruction-following tool that's ready to tackle specific, complex tasks.
And the goal of SFT is alignment with human instructions. When researchers are building their SFT datasets, they seem to follow really different strategies when it comes to scale. What are the pros and cons of this minimalist versus maximalist approach?
The strategies really reflect different goals. The minimalist strategy, which you see in projects like Limo with only 800 examples, or S1 with about 1,000.
1,000 samples.
Right. They prioritize ultra-high quality and really precise data curation. Their goal is often to prove that you don't actually need massive computational resources if you can just identify and distill the most potent cognitive templates for reasoning.
But wait a second, 800 examples sounds ridiculously low. Is that really generalizable, or does that only work for very specific, stylized reasoning tasks that are easy to template? What's the hidden cost?
And that is the trade-off. Minimalist sets can prove the concept of high-quality data. They can demonstrate reasoning power on clean, isolated tasks. But to handle the messy, noisy, ambiguous problems you find in the real world,
To get general robustness.
you need volume. And that's the maximalist strategy. Projects like OpenThoughts 3 scale up to 1.2 million samples. This huge, diverse volume is what's necessary to hit the true state-of-the-art performance ceilings, to enhance robustness, and to make sure the model can handle the wide variety of instructions it's going to see in the wild.
So if your goal is a commercial, robust agent, the maximalist route is basically non-negotiable right now.
It is.
And just like with pre-training, The data needs to reflect the real-world challenge. The real world isn't about isolated functions, it's about massive software repositories.
Correct. The ultimate challenge is enabling cross-file dependencies and long context reasoning. And this is what led to the creation of repository-level SFT datasets, mainly the SWE family.
SWE-Smith.
So SWE-Smith gives you pipelines to generate task instances from GitHub. SWE-Synth creates verifiable bug fix data, but crucially, SWE-Gym provides Python task instances with their own executable runtime environments.
Why is SWE-Gym so significant?
SWE-Gym is critical because it forces the model or the agent to learn the entire process of development, not just code generation.
So it's not just write this function.
It's resolve this ticket. It includes setting up the environment, reading documentation, running tests, debugging based on the output from those tests, and then committing the fix. It moves the training scope to a much higher level, which is the foundation for training truly autonomous agents.
Okay, let's get to the gold standard, the hyperparameter recipes. The sources laid out this extensive experiment comparing a dense model, Qwen 2.5 Coder 14b, against a sparse MoE model, Qwen 330b A3b. What did that side-by-side teach us about tuning?
This comparison is just invaluable. It gives us a practical blueprint for optimization, and it really highlights how different the needs are for dense versus sparse models during SFT.
Let's start with epochs, the number of times you run through the data set. How did their learning curves compare?
The difference was really stark. For the dense model, the Qwen 2.5 Coder, performance gains were massive and rapid in the first few epochs. It stabilized very quickly. It usually hits peak performance within 5 to 10 epochs.
So it's sample efficient and stable.
Very. On the other hand, the MoE system showed much lower performance at the start and required this prolonged, sometimes tedious training period. It needed up to 10 epochs or even more to stabilize and actually realize its potential.
And that means a higher total computational cost in training hours.
A much higher cost.
Why does the sparse architecture need that much longer to cook?
The source suggests that MoE systems just have a more complex optimization landscape. You have to train the thousands of expert weights, and you have to train the specialized router weights that decide which expert to use.
So two systems learning at once.
Exactly. And that combination just requires more time for the router to learn its mapping and stabilize so that all that extra capacity is actually being used effectively.
What about the learning rate?
The practical sweet spot for the learning rate, or LR, for these models was found to be in this really tight band between 5 times 10 to the minus 5 and 1 times 10 to the minus 5.
It's a very narrow range.
Very narrow. The researchers found that moving outside that range led to either rapid performance drops or just excessively slow convergence. So that's a critical starting point for any practitioner.
But the choice of the learning rate scheduler revealed a key instability that was unique to MoE systems, didn't it?
Yes, and this is maybe the most crucial recipe detail for training sparse models. For dense models, schedulers like cosine or linear decay work great. But for MoE architectures, constant LR schedules consistently did better than decaying schedules.
Okay, explain the routing instability this fixes. Why does aggressively decaying the learning rate hurt MoE?
So when the learning rate decays aggressively, the weights of the experts, that huge pool of parameters holding the model's knowledge, they start to move very slowly. But the router weights, which are much smaller, continue to change.
So they get out of sync.
They get way out of sync. If the router changes too quickly compared to the slow-moving experts, it might start consistently picking suboptimal experts. Or worse, it could just route traffic away from the most useful experts, essentially killing them off.
So maintaining a constant LR keeps the router and the experts optimizing in a stable, synchronized way.
It ensures that the full capacity of the MoE system can actually be realized. So the final conclusion on SFT is a really clear practical mandate. Dense architectures are stable and sample efficient, they're predictable.
But MoE backbones offer superior theoretical capacity.
They do, but they demand a much higher tuning cost. Specifically, they need prolonged epochs and these constant LR schedules to overcome their inherent optimization fragility.
SFT teaches the model how to produce code that looks right, that follows the instructions. But that doesn't guarantee it actually works.
It doesn't guarantee correctness at all.
So the next major step is reinforcement learning, RL, which uses feedback from the environment to teach the model to be correct.
RL is the ultimate alignment for functional success. But as you said, it is completely dependent on supervised fine-tuning. SFT is the necessary precursor.
So SFT solves the RL bootstrapping problem. How does that problem manifest if you try to start RL too early?
Well, if you start RL training from a general pre-trained Model 1 that knows language but hasn't written much code, the search space is just impossibly vast. It's like trying to learn how to debug a kernel by just randomly guessing. SFT is critical because it initializes the policy with a strong prior. It already knows basic syntax, common APIs, semantic patterns. And that strong prior dramatically constrains the search space, which makes the exploration that the RL agent has to do actually feasible.
And the cutting-edge recipes are actually blurring the line between SFT and RL, right? Turning it into this continuous self-improving loop.
That's the iterative cycle of self-improvement. The RL agent interacts with the environment. It writes code, runs tests, tries to fix things, and the successful trajectories it discovers,
The ones that work.
the sequences of reasoning and code generation that maximize the reward, those are collected. This high-quality data is then used to create a new dataset for another round of SFT.
So you're distilling the experience back into the model's core parameters.
Exactly. You're teaching the model what you learned from interacting with the world. Projects like SWEX use this cycle for continuous refinement.
Let's define the core mechanism here. Reinforcement learning with verifiable rewards, or RLVR.
RLVR is so powerful because it optimizes the model based on a reward signal that's tied to objective, verifiable outcomes, passing a unit test, getting a successful compilation. Instead of relying on subjective human feedback, you're relying on concrete correctness.
And that surgically concentrates the probability math on the reasoning paths that lead to success.
Precisely.
This obviously requires specialized datasets that have rigorous test cases. What are the foundational resources for RL training?
Right, you need data sets where correctness is unambiguous. Code contests is a big one. It has about 13,000 competitive programming problems, each with human solutions and comprehensive test cases. TACO aggregates over 25,000 problems.
But for maximum rigor?
For maximum rigor, the research points to Clear Code Test. This was built using a generator and checker framework, resulting in almost 28,000 problems with rigorously synthesized and validated test cases designed to cover critical edge cases. That makes them exceptionally reliable for calculating rewards.
What are the measurable performance gains we see from applying RLVR? Are they worth the effort?
Oh, the gains are substantial, and they often close the gap between smaller, well-tuned models and massive proprietary ones. Ace Coder, which is built on a 7 billion parameter model, reported gains of about 10 to 25% on benchmarks like HumanEval and MBPP.
That's a huge jump.
It is. And DeepCoder, a 14 billion parameter model, achieved a 60.6% pass rate on Live Code Bench after RLVR tuning, which is performance that matches much, much larger proprietary models. It shows that intelligent optimization can make up for a big lack of raw scale.
So let's get into the anatomy of that reward design. Correctness is primary, but for real-world deployment, you also need quality and safety.
We categorize rewards into two necessary pillars. First, correctness-oriented rewards. These are objective signals from execution pass-fail or from static analysis tools. A linter, for example, can penalize code for style violations without even running it, which provides a crucial intermediate reward.
And the second pillar handles the broader standards you'd need in a production environment.
These are the quality-oriented rewards. They enforce standards beyond just function. So, task alignment rewards can quantify the similarity between the original instruction and the code to make sure the model didn't solve the wrong problem correctly.
And crucially, security.
Crucially, security and robustness rewards. These systems integrate security tools that actively penalize code that contains common vulnerabilities like SQL injection or cross-site scripting.
So the output of the security tool becomes a negative reward.
It becomes a strong negative reward, training the policy to actively avoid generating insecure patterns from the start.
What's surprising is that this whole refinement process, it isn't about correcting every single token. The research showed that the gains from RLVR are driven almost entirely by optimizing the model at a very small fraction of high-entropy tokens.
Right.
Are these the forking tokens you mentioned earlier, the critical decision points in the code?
Precisely. These are the moments in the reasoning process where the model has high uncertainty, where multiple equally probable next actions exist, deciding whether to call API A or API B, choosing between two different algorithmic approaches.
And RLVR focuses its energy right at those forks in the road.
Exactly. By concentrating the probability mass on the few known high-reward paths at those critical decision points, the model's overall success rate is boosted dramatically. It proves that RL is about precision policy refinement, not just brute force data collection.
So the final step in this whole recipe is taking that highly optimized, verifiable model and wrapping it in an operational system. the
What?
autonomous agent. This is a system that can actually execute steps, interact with the dynamic environment, and self-correct.
It's the full package.
Let's look at the operational blueprints for these agents.
Well, the simplest blueprint is end-to-end orchestration, which often models a sequential workflow, kind of inspired by the old waterfall software development method.
So like ChatDev and MetaGPT.
Exactly. They use multi-agent collaboration. They assign specialized roles, a CEO agent for planning, a developer agent for coding, a tester for verification, and they coordinate them using standard operating procedures to complete a project sequentially.
But the truly transformative agents are the ones that integrate code generation into the reasoning process itself, the thinking agent. This is where code becomes a tool for verification.
That's the thinking in code concept, and it's all about maximizing precision. This includes approaches like program-aided language models, PAL, and program of thoughts, POT. These systems don't just output the final answer.
They output the process.
They generate executable Python code to perform all the intermediate mathematical, logical, or algorithmic steps.
Give me an example of how that execution actually enhances the reasoning.
Okay, imagine the task is a complex math calculation, say integrating a function. A traditional LLM might try to solve it with text and just hallucinate an answer. A parallel agent, on the other hand, generates Python code that calculates the integral, executes that code in a secure environment, and then uses the objective, verifiable result from the Python interpreter as the next step in its reasoning chain.
So it's fact-checking itself with code.
It's using external execution for objective verification, which pure textual reasoning just can't match.
What key capabilities define an advanced agent in practice today? It has to be able to handle the complexity of large professional code bases.
Absolutely. First, the capability for repository-level context is crucial. The agent needs to index and retrieve symbols and dependencies across thousands of files. Augment is an example that uses a powerful context engine for this.
What does that engine do?
It often relies on static analysis tools to build a map of the entire code base, where functions are defined, how classes inherit, what external libraries are used, and that allows the agent to maintain global consistency when it's making edits across multiple files.
And second, they have to interact with the world the same way a developer does, through a command line.
This is terminal and tool use. Terminal agents like OB1 operate directly in shell interfaces. They translate high-level instructions into executable command line code. The Codact framework takes this even further by treating executable Python code as a dynamic action.
So the agent can combine tools.
It can store intermediate results, combine system tools like Git and compilers and debuggers, and it even has self-debugging capabilities using an interpreter right inside its own environment.
And finally, we see agents offering full process automation, tying all these pieces together.
Right. Refact Agent is designed for that full process, from parsing requirements all the way to deployment. It uses retrieval augmented generation, RA, to get project-specific context. It supports over 25 languages, and crucially, it synchronizes with standard developer environments, Git, and CI/CD pipelines.
So these agents are designed to execute entire feature implementation plans, step by step.
That's the goal.
Given this level of autonomy executing code using
Wow.
terminals, fetching data, the security stakes are incredibly high. The recipe for deployment has to include a robust safety recipe, defense in depth.
It has to. And that defense-in-depth approach requires 3 non-negotiable layers. Layer 1 is execution isolation, containment.
So secure sandboxes, but the source suggests we need to move beyond static sandboxes.
Correct. The basic requirement is a secure environment, usually Docker. But the state-of-the-art is dynamic containment. Frameworks like Projit introduce programmable privilege control.
How does that work?
The system dynamically assesses the risk of the agent's proposed action in real time. If the agent wants to do a harmless file read, it gets low privilege. If it wants to access the network or write to critical system directories, the policy dynamically tightens the restrictions, minimizing the blast radius of a bad command.
Okay, layer 2 is proactive vetting, catching errors before execution. This feels like the most critical security layer. How does this Critic LM agent provide a blueprint for fixing problems?
This is the tool-in-the-loop strategy. You have specialized security agents, the critics, that use modern security testing tools, SAST and DAST. When the primary agent generates code, the critic reviews it and flags vulnerabilities like SQL injection.
But it doesn't just say, this is bad.
No, and that's the key. It structures its findings into a specific, formalized repair prompt for the primary agent. The prompt might use JSON or XML, detailing the exact vulnerability, the bad code, and giving explicit instructions like, you must sanitize this input variable using the standard library's escape function.
So it teaches the primary agent how to self-remediate before the dangerous code ever runs.
Exactly.
And the final layer, layer 3, is runtime oversight, real-time policy enforcement.
This is handled by Guardian agent frameworks like Agent Sentinel or Llama Firewall. They enforce safety constraints in real time, monitoring every command. The most advanced systems, built on agent spec, enforce verifiable policies.
What's a verifiable policy?
It's a formally defined rule, like the agent is strictly forbidden from executing commands that modify the file system outside of project root, or the agent can never use the sudo command.
And if something goes wrong.
For maximum reliability, systems like CentrealESE provide active control, allowing for immediate intervention and rejection of an unsafe action, coupled with the ability to roll back to a previous safe state. All 3 layers, isolation, vetting, and oversight, are essential for a secure production deployment. So, to summarize this deep dive into the practical recipes of the code intelligence era, we really covered those necessary architectural trade-offs. You have maximizing raw capacity with MOE, or prioritizing efficiency and long context with recurrent and hybrid designs.
Right. And we established that the data foundation requires strict decontamination protocols like you see in StarCoder data, and that specialized objectives like fill in the middle are absolutely vital for IDE utility.
And most critically for training, we define that distinction in optimization. Specialized scaling laws have to guide how you allocate your compute budget across languages.
And getting to verifiable correctness demands a 2-stage alignment process. SFT provides the strong prior you need to solve the RL bootstrapping problem.
And then RLVR uses those verifiable rewards from rigorous datasets like clear code tests to surgically optimize the model's policy at those critical forking decision points.
The culmination of all these recipes is the autonomous agent, which, by necessity, must be deployed with that 3-tiered defense-in-depth security strategy dynamic isolation, structured proactive vetting with critic LLMs, and real-time runtime oversight.
That's the blueprint.
So what does this all mean for you? The development of code LLMs is no longer a research curiosity. It's an engineering challenge. It's focused on building robust, verifiable, and secure autonomous systems through highly intentional data design and this sophisticated multi-stage alignment.
And finally, we noted that even highly capable proprietary models like GPT-4o sometimes exhibit this strange inverse scaling effect on moderately difficult problems. They prefer their own internal textual reasoning over using a superior external tool like the code interpreter.
So they get overconfident in their own internal thought process.
Exactly.
That's a fascinating vulnerability. The smarter the model gets, the worse its decision-making can be sometimes.
Yes. And that leaves us with a provocative final thought for you to consider. As we continue to engineer these code agents, what decision-making strategy will ultimately prove to be the most reliable for complex, real-world development tasks?
Is it maximizing pure internal confidence through dense training?
Or is it ensuring that external verifiable execution is always prioritized at those critical junctures? The future of secure and reliable software development may very well hinge on the architecture of that confidence mechanism.
A truly challenging problem for the next era of coding. Thank you for joining us for this deep dive into the recipes of the code intelligence era.
Thank you.
We'll catch you next time.